Nobel laureates in physics and chemistry, laureates in economic sciences, members of the Academy, ladies and gentlemen. The role of science is to question what is regarded as the truth, to uncover hidden phenomena, to see the possibilities which are obscure to the ordinary mind. The passionate observer, equipped with imagination and creativity, leads us forward to a world with better conditions. We stand on the shoulders of giants. As science develops, new giants appear and show us the way forward. Some of them are with us today. The progress of mankind is very much connected to materials, the way natural materials can be exploited and used, and how new man-made materials can be developed. Materials have even given the names to the ages of civilization, the Stone Age, Bronze, Iron, Silicon ages. Man is not able to do anything without materials. It is essential to understand the properties and uncover the hidden secrets of materials and unexpected states of matter, and to be able to design entirely new and intelligent structures constructed using the smallest possible building blocks. Today's intelligent man-made materials would have been pure science fiction just 50 years ago. It is not possible to plan for the unknown. New fundamental discoveries that may lead to applications which could not be foreseen, and the period between a fundamental discovery and eventual applications is often very long compared to the criteria commonly used by governments and funding agencies. But with the words taken from Vannevar Bush, the American engineer and science administrator, as long as scientists are free to pursue the truth wherever it may lead, there will be a flow of new scientific knowledge to those who can apply it to practical problems. During the last century, we have witnessed an explosive growth of science and technology, a development nobody could even dream of at the beginning of the last century. The French advocate of enlightenment, Jean-Antoine de Condorcet, he argued that the expanding knowledge in the natural sciences would lead to progressive development of human capabilities and lead to a world of individual freedom and moral compassion, since, as he believed, social evils are the result of ignorance and error rather than an inevitable consequence of the human nature. In this respect, he seemed to be too optimistic when it comes to how humans treat each other. We still see corruption, dishonesty, and unethical conduct in otherwise well-developed societies. However, new theoretical tools for properly designed and formalized negotiations help us to deal with conflicting interests. Today, science and scientific knowledge are needed more than ever. We live in a time with widespread resistance to knowledge, where even powerful world leaders deny scientific knowledge. A new term, post-truth, has been added to the Oxford Dictionary, meaning how emotions affect people more than facts. We need to trust in science, because only knowledge can make the world better. Alfred Nobel, he recognized the importance of science and those who uncover what has been hidden, who explain our mere existence, who improve the quality of our lives, who open doors for future findings. This week is the big celebration of science. And today, you are all welcome here to listen to some of those who have increased our knowledge and made a difference to the way we think. I will now ask Professor Thors Hansson, member of the Nobel Committee for Physics, to introduce the Nobel Prize in Physics.
So, good morning, everybody. So I'm very happy for this opportunity to say a few words about the Nobel Prize in Physics 2016 and introduce the laureates who are going to give 2016 Nobel lectures in physics. So here they are. I'm sure that many of you already know their names. It's David Paulus from University of Washington, Seattle, USA. It's Duncan Haldane, Princeton University, also USA. And it's Michael Kostelitz, Brown University, United States. So the citation of the Academy that motivates the prize is for theoretical discoveries of topological phase transitions and topological phases of matter. And I will not make any attempt to explain what that means to you. You will hear 2 lectures later that will try to explain to you what that means. Okay. So I will instead say just a few words about the laureates. So I start with Professor David Paulus. He was born in the UK, 1934. He got his PhD from Cornell University in the United States, and he's now the emeritus professor at the University of Washington, Seattle. And I should tell you that Professor Paulus is a legendary person among condensed matter physicists. So he has made really groundbreaking contributions to theoretical physics. I will not take time from the lecture to list all his achievements. But I should mention that although he's awarded this year's Nobel Prize for his work on topological states of matter and topological phase transitions, many physicists might hold the view that his work on mesoscopic physics, where he introduced the very central concept of Paulus energy, might be as important as the work that we are celebrating today. His achievement has earned him many prestigious awards, including the Maxwell Medal and Prize, the Wolf Prize for Physics, the IOP Dirac Medal, and the Large Onsager Prize. Now, I already mentioned that I already read the citation, and as you can see, it has 2 pieces to it: topological phases of matter and topological phase transitions. These 2 subjects are intellectually closely connected, but they are still distinct, and they are going to be presented in 2 lectures by the 2 other laureates. And the first one will be given by Professor Haldane, and I will now say a few words about him. So he was born in London in 1951, got his PhD from Cambridge University, but ended up as the Eugene Higgins Professor of Physics at Princeton University, where he is now presently and still very, very active. And he has worked in many areas of theoretical physics. Again, I won't give any long list, but just mention that in addition to the work that we are honoring today, he has introduced important concept in physics, the concept of eluting a liquid, the concept of fractional exclusion statistics, and the concept of entanglement spectrum, and he has given seminal contributions to the theory of the quantum Hall effect. So now it's my pleasure to, I should say also that he's been awarded the Maxwell Medal and Prize, Oliver Buckley Condensed Matter Prize, the ICTP Dirac Medal. And now I will call on Professor Haldane to come up and give the first of the 2016 Nobel Lectures in Physics. Please, Professor Haldane.
Thank you. This is a rather challenging lecture for me to give because usually I give these talks to specialists, but I'm going to make an effort to give you some flavor of three kind of surprising discoveries that both David Paulus, who I'm going to talk for a bit, and myself have made. And these are all things which I think were not expected at all at the beginning of whatever calculations were done to reach these things, and they all emerged as surprises. And I heard from Marcel Denys about this, David's work on this thing, and it's again a similar thing that they didn't realize what good stuff was going to happen until almost the end of the calculation. Okay, so I thought I'd give a little bit of background for what I'm going to do, because I'm not sure who I'm talking to. But of course, you just recall high school chemistry. You've got orbitals that get filled. I've probably gone one back before. Yeah, sorry. You have a set of energy levels in atoms that quantum mechanics makes discrete, and you can get to fill them up with electrons. And in the usual case, you can put 2 electrons in each orbital because they have something called spin, which goes up and down. And I'm going to make an analogy for this because this is actually what's going to happen in the quantum Hall effect. And the simple case of the integer quantum Hall effect, we have a 2-dimensional surface on which electrons can move with a large magnetic field going normal to the surface. And in a magnetic field, electrons go around in little circles, just like in the atom. But now it's the magnetic force that drives you in a circle, the force at right angles to the motion of the electron. And in this case, as the radius of the orbit gets bigger, that corresponds to larger kinetic energy of the electrons. So in that case, we have, again, an energy level diagram where we can fill up the orbitals. But instead of having, as in chemistry, a 1s orbital, a 2s, and a 2p, and then 2d, we actually have a large number of orbitals. And in the quantum Hall effect, the integer quantum Hall effect, the number of orbitals is macroscopic. It's proportional to the area of the system, the area in which the electrons are able to move. And there is one independent orbital for every quantum of magnetic flux that passes through the area, the system. So that, in case you haven't seen any of this stuff before. So if I have a fixed density of electrons, let's choose, because the number of orbitals in each of these levels degenerate levels is proportional to the magnetic flux density, the magnetic field. We could choose the magnetic field just right so we can completely fill up the lowest set of orbitals here, the lowest Landau level. We call these degenerate set of orbitals Landau levels. And if I take this system where I just tune things just right, so there's exactly the right number of orbitals to be completely filled by the electrons in the lowest Landau level, and the others are all empty, we get something that appears initially to describe the integer quantum Hall state that turns out to be the earliest of the topological states of matter that were experimentally found, and that was found by Klaus von Klitzing in 1981, and very quickly, because of the implications, it led to his Nobel Prize in '85. So when you have this situation, you've got an energy gap. If you're a chemist, you'd call it the HOMO-LUMO gap or something. And so this is a kind of rigid system that you filled it just up to this level. It's going to cost you energy to put any electrons in a higher level. And so if I try to squeeze the system, where I'm actually changing the area in which the electrons are allowed to move, and therefore changing the number of orbitals, if I compress this thing down, I will not be able to compress it any further than having filled this Landau level up completely, because I'd have to, if I pushed it together more, I'd have to put things in the next Landau level, which costs me a lot more energy. So at first sight, it looks that's a very fine-tuned thing that you'd have to get everything just right. And the special feature of the Hall effect that von Klitzing found is it's very robust. But actually, this is a topological system, and because something has to happen at the edge, you don't actually need to fine-tune anything to get this just right. Because at the edge of the system, if I think about the electrons going around in little, do I have a light here? I can't see it. Yeah, if they go around in little circles, I've drawn them going around in clockwise circles here. But if they actually reach the edge of the system and try to go around in a clockwise circle, they go bang, and they will bounce back off the wall. So in the orbits that hit the wall will actually precess around the wall in the anti-clockwise direction. And that's one of the hallmarks of topological systems. They have strange states at the edge of the system. And this is what we call the edge states. They're counter-propagating edge states that have this remarkable feature that they only allow propagation around the edge in a single direction. And of course, that's because if they can only go one way, it means if I looked at the thing backwards in time, they'd be going the other way. And this is a system with what we call broken time reversal invariance. The magnetic field breaks the symmetry of systems under the change of direction of time. So the orbitals at the edge actually go up a little bit, and therefore there's a reservoir of electrons at the edge. The Fermi level is the highest occupied state, the chemical potential, and as I change the magnetic field, I will be changing how much I fill this thing up at the edge, but I will still maintain the gap in the bulk of the system. So this system does have gapless excitations at the edge. There's a gap which is very small. It's proportional to the length of the 1 over the length of the edge, so it's a microscopic gap at the edge of the system, but I still have in the interior this large bulk gap, which is a topologically protected state. Well, what von Klitzing found, he did these measurements of, he measured the Hall resistance, the Hall resistivity, but I'm going to talk about the Hall conductance, which is 1 over that. So what he sees in the picture, you change the magnetic field, and the Hall conductance sticks at various values, which turn out to be quantized, and it turns out to be an integer times these fundamental constants e squared over h, or e squared over 2 pi h bar. And being an integer is what finally got understood to be a topological property. Topology, we heard from Hansson at when the prizes were announced about you're counting the number of holes in bagels and things, and those can't be other than integers. These are topological properties that we'll see. And this is actually what a very nice result of David's has been. Okay. So the von Klitzing system is much dirtier than the theoretical toy model I presented to you. It's got all kinds of details of junk inside it. And the work at the early 80s focused on these difficult problems of how you treat disorder and randomness and what was going on. But the work I'm going to tell you about of David's is he had the idea to study not the effect of this kind of random dirty system, which is difficult, but just a simple periodic system, add a kind of crystalline background of his choosing to these Landau levels. And Marcel Denys, who worked on this, said at the end of the day that was David's brilliance in the thing that he actually chose a tractable problem as opposed to sticking around the physically relevant problem was apparently the disordered one. And we have this sort of situation. The ideal case where it's clean in the middle is perfectly flat. And this is a case where Bob Laughlin, who won the prize a little bit later for the fractional quantum Hall effect, had earlier given an extremely powerful argument that says if I have this flat system in the bulk and the only places where there's energy levels at the Fermi level or at the edges, then if you apply this electric field to make things flow, the charge would flow across the system in a way that couldn't be affected by any kind of dirt because it was too far for any scattering between points at one Fermi energy and the other Fermi energy. And so here there was a very clear argument that related a gap in the bulk region of the sample to this perfect quantization of the whole conductance, where it's just given by a whole number times fundamental constants. So the actual problem that people trying to be practical or trying to be realistic would have tried to solve is this one here, where there's a lot of junk in the middle and a dirty potential. But as I said, this is very difficult, and what David took some very beautiful results from Hofstadter and solved this problem here, which should be a perfectly periodic wave in the middle. The potential is periodic, which means some points the lowest state in the system will be down here, and the highest state will be at this point. So the lambda level, which in this case is a perfectly flat, infinitesimally thin energy level, gets smeared out into a range of energies between the top and bottom of this periodic potential. And that's this so-called TKNN paper, the Paulus, Komoto, Nightingale, and Denies. I guess some people trying to be cute put TKNN squared like that, but the other three were three postdoctoral collaborators. Komoto was David's postdoc, and Nightingale and Denies were other people's postdoc, I guess, at University of Washington, Seattle. Anyway, they together with David, they looked at this problem of what the presence of this simple periodic potential added to the Landau levels would do to the integer quantum Hall effect. And the bottom line is they discovered a remarkable formula that they hadn't been looking for, and that, according to Marcel Denies, it jumped out of them only at the very end of the calculation. Okay. They were too concerned with the details, but at the end they suddenly saw something was important. So David had been particularly interested in this very interesting toy model a lot of people were kind of fascinated with at the time. It often goes by the name of the Hofstadter Butterfly, because you had an extremely beautiful pattern come out, and Douglas Hofstadter found this in the 1970s, and he loved his aesthetic appeal, I guess. It's a model of a crystal in a magnetic field, and people have gone to town on this model because it's got all kinds of beautiful features in it. But basically, it's just the same model as before: kinetic energy of particles in a magnetic field, and then of just the simplest possible periodic potential, a cosine potential in the x direction and a cosine potential in the y direction added together. And this thing's called the butterfly. It's usually shown rotated sideways, and I guess it's got tremendous amount of fine structure and fractal structures floating around in it. But that's not what's interesting us here today. It has these very narrow levels, which I guess for the purposes of calculating the whole conductivity, this is done by Yossi Avron and his former student. They donated this picture to me, so there's no copyright concerns in my lectures. And so the numbers here tell you what this integer should be. Here at the bottom, this thing is not the Landau levels, but it's very close to the Landau levels structure. It's almost identical to what you would see for a simple Landau level structure. And you've got a lot of very narrow levels, and when you fill the first one, you get one filled level, the second one two. But when you look in this other structure, you get all kinds of other weird numbers floating around. And they got fascinated, the team got fascinated and saying, first of all, how can you calculate these numbers, these integers? What are they? And so the basic point that Marcel tells me that David pointed out was that Laughlin's argument tells you if you've got a gap in the bulk of the system, you've got to get this integer quantization coming out. And Laughlin had done it for the simple Landau level case, but this thing also has gaps in the bulk, and if the chemical potential's in there, you should get quantization. And they were struggling to find out what was the formula that get these integers. Okay. And so after they solved lots of equations and found the thing, they realized they found how to calculate these integers. They found there had to be a more general principle than just solving what were called Diophantine equations, some mathematical structures. And basically, if you take you've got a periodic potential, it's actually not the usual kind in the crystal, because there's the periodic. The unit cell you have to use is not the simple one of the cosine potential. It's related to how many of the unit cells contain an integer number of magnetic flux quanta. So it's a rather strange band structure. But basically, if you've got something periodic, there's a Bloch theorem that says you can write the wave function of an eigenstate of a system in a periodic potential as two things, a periodic function times an exponential e to the I k dot x or k dot r. And the details of what's going on in the bands are all contained in this periodic thing. So they took a very standard formula, a fundamental formula for the calculating the conductivity of a system called the Kubo formula, and plugged this stuff in. So the Kubo formula is usually used for calculating the dissipative part of the resistance. But in the case where you're looking at this Hall resistance, where you're looking at the response to an electric field which is parallel, which is at right angles to the motion of the current, so it doesn't dissipate any energy, you get different formulas. Well, they put this in and they cranked the handle, and they eventually got a very nice formula. They didn't actually comment on it in the paper, that how nice this was in some sense, but they ended up with a formula that depended only on the details of the band structure, which are of the wave functions of the band structure, which are contained in this function here. There's no reference anymore to the energy levels of the problem. The energy levels are there in the Kubo formula, but after integrating stuff out and using formulas for the velocity of the system, you find the energy levels when you're calculating this Hall conductance, this one which is dissipative, not the usual ohmic law conductance. The energy levels all drop out. So this was the first form they got of a formula, and after I'll show you in a minute how this turns into an integer, but they found this formula which gave you the Hall conductance, which is these numbers e squared over h, which is von Klitzing's number of 25,310 ohms, I guess. Ohms to the -1, sorry. And then we have these numbers here, which you can do some simple mathematics with Stokes' theorem on. So they found this formula. And shortly after they published their paper, another very influential discovery in physics was that Michael Berry discovered that the adiabatic approach to quantum mechanics had missed out an important geometrical phase, and in fact this is another piece of work that a lot of people think should get the Nobel Prize. This is my hint to the committee. But it's geometric, so I guess you can say it shouldn't have come this year. Anyway, that's my. So Berry's example was a spin which was polarized along some axis, and you gradually rotate this, and you find that you pick up this additional phase, which is very geometrical. It's actually the solid angle, the spin times e to the I times spin times the solid angle enclosed by the path, which is ambiguous modulo 4 pi. And therefore the spin has to be an integer or a half integer, which we knew for other reasons. But these are typical of these topological things that have interesting consequences. This tells you that spin has to be quantized, for example, even if you didn't do it by algebra. So anyway, the mathematical physicist Barry Simon, in 1983, just after the two papers had been published, I guess he recounts that someone else tipped him off about this connection, and he should look at it, or there had to be a connection. And he found that the two things matched together very well, that the Paulus, the TKNN expression was an integral over a curvature associated with this phase of Berry's, this holonomy. And mathematically, it was an integral over a compact manifold, which turned out to be the Brillouin zone, which is topologically equal to a torus. And in fact, he pointed out this connection to what is really a mathematical extension of Gauss's famous Theorema egregium, which I guess he discovered while he was a foreign member of the Royal Swedish Academy of Sciences, because he was joined in 1821, and this is 28. And he thought, I think Gauss seems to have thought this was the most amazing discovery he ever made in mathematics. So what Gauss discovered was what we heard from Thor Hansson about the bagels and the thing. So Gauss discovered something that you can easily get the simplest version of it from your high school algebra class, right? So you know that the surface area of a sphere is 4 pi r squared, where r is a radius. And the Gaussian curvature that Gauss introduced, of course, for the sphere is uniform, and it's 1 over r squared. So if I integrate the Gaussian curvature over the surface area of the sphere, I get 4 pi. But what Gauss discovered as this amazing theorem was that I can change the shape of the sphere to anything else, like a football or a banana or whatever, and they still got 4 pi. And this is called the Gauss-Bonnet theorem, I guess because Gauss never wrote it up properly and Bonnet put all the details in later. So if I take this thing, we get this by now famous account of the Swedish and the German pretzels, and we also get the account that the famous relation between coffee cups and bagels, you have a mug is the same as a ball. What's been called a loving cup is the same as a Swedish pretzel, and I'm not quite sure what kind of loving cup this is because it's got 3 handles, but that's the same as a German pretzel. That doesn't I thought, well, I'm not sure if that's in the right nationality kind of combination, but anyway. So this is the topology that you see everywhere when people give talks about topological insulators. They love the coffee cup. I'd like to see actually the Swedish pretzel changing into the loving cup and backwards, rather it be a change from the coffee cup and the bagel. So, okay, the formula that they found, that Barry Simon pointed out that this formula was really the first Chern class integral. Well, basically, it can divide into 2 parts. It's 2 things. It's the integral of a curvature, which you can write as an antisymmetric tensor, but now in momentum space, not in real space, or K space, block space. And then this is the formula. The other part of the formula is the formula for the Berry curvature. And in fact, it's kind of interesting fact that, again, talking about things which are discovered before their time, this formula is in a very correct paper, or something like this formula, a 3D version, which is non-topological, is in a 1954 paper by Paulus and Luttinger that was denounced as completely wrong and nonsense for many, many years. Only in 1999 was it recognized that it was actually a case of Berry curvature, and somewhat later it was shown to be essentially correct in a lot of situations it's been applied to. So this, again, topology formulas are not obvious until so I guess Barry Simon did a very big contribution in pointing out the mathematical framework of what David and the other collaborators had found. So just quickly, in these formulas, if we write them down, people make a big correspondence now to think of things like something like electromagnetic fields in momentum space, because the curvature is kind of like the magnetic field, and the curvature can be written as something like the curl of a vector potential, which is called the Berry connection. And the Berry's phase is the integral of the Berry connection around the closed path. And it's very much like the Bohm-Aharonov phase when you take an electron around the loop and in the presence of a magnetic field and try to calculate what phase it picks up when it goes around that loop. And the Berry phase, because the Berry phase is e to the I something, this is a number which is only defined modulo 2 pi. From this, you quite quickly see the mathematics of Stokes theorems tells you that the integral of the curvature over something bounded by a curve has to be 2 pi, has to be 2 pi times an integer. So this was the form that Paulus found. The actual form they wrote in their paper looked something like this. They'd integrated by parts the first formula, and then they found, but this thing has to be, when you do the mathematics, is obviously an integer times e squared over h. And that was the thing. So, in fact, as I said, Marsfeld and Ice told me that this only emerged at the very end of the calculation. It was kind of afterthought. He has some talk about they realized there was an elephant in the room after looking at their formula. There had to be something a lot more in their paper than just the actual values of these numbers in this nice, colorful diagram, right? The numbers, of course, were not interesting, really. I mean, the only challenge is that you can compute them, but then the big picture, rather than being interested in Hofstadter's butterfly, the big picture is to come out with a very fundamental formula that no one had expected existed before. And this is this amazing work that he did. Okay, so this is right. So out of this, my own work, which was also mentioned, a bit later comes from seeing that this integer quantum Hall effect can actually occur without Landau levels. So maybe you could say this was implicit in the TKNN result, but I don't know, it wasn't noticed. The 1982 paper was all about the periodic potential on Landau levels, and it hadn't really been appreciated that if it's a topological thing, then the details surely can't matter, and the specific realization in terms of Landau levels is very complicated and not very practical for hopefully finding new materials, right? And so I was, again, stumbled over this feature that you could actually write down a very simple model that turned out to be very influential because you can do very simple calculations with it. It turned out to be something like graphene. It's a modified form of graphene where you have second neighbor, electrons can tunnel between second neighbors and they pick up a little bit of a complex phase, which is a time reversal breaking effect as they hop around. So you end up with an extremely simple kind of so-called tight binding band structure. And it turns out to really be the first of the topological insulators. This is a time reversal broken topological insulator, which in my view actually has more potential, practical potential than the normal kind that people are studying a lot now. But we'll see what happens with this. So this was actually it's kind of graphene. At the time, we didn't know that someone would invent graphene by taking a Scotch tape and on pencil, scraping a pencil over something and doing Scotch tape. So I put in my paper that this would be a single monolayer of graphite, but it would be inconceivable for someone to actually realize that. And of course, I think the lesson is that material science can take us to play. If it can be done, someone will do it, right? However crazy as long as it's not real black holes and something like that, whatever the crazy model you come up with, if it's just something interesting, it's most likely someone will be able to make something that does it, whether it's cold atoms or the other ways. So one of the features of these systems is that they have this one-way channel around the boundary where things move in one direction. In the Landau level case, that was really coming from the direction of the magnetic field. But in graphene, if you look at it, graphene, you call an edge of graphene. There's various edges, and there's a nice one called the zigzag edge mode. And you find that graphene has itself at the edge. If I take a view along the edge, there's actually a bound state which goes between two different Dirac points in graphene and exists in part of the surface Brillouin zone. And it connects these things. Once you can open up a gap in graphene by turning it from a semi-metal to a semiconductor in two ways, by breaking inversion symmetry or breaking time reversal symmetry. When you break inversion symmetry, you get something boring. This state has to be attached to either the top or the bottom band. In the boring case, both ends of the state are attached either to the valence band or the conduction band. But in the interesting case, one point ends up attached to the conduction band, the other to the valence band, and there's a kind of channel, a plumbing connection between the two that you can drive states up and down by putting a magnetic field through this flake of graphene-like substance. And if I fill the system up to the Fermi level that's in the gap, I find I have these things that travel one way. This is actually the hallmark of the topological states. They typically have something very interesting at the boundary. And the start of all, about 10 years ago or 12 years ago, Eugene and Amelie and Charlie Kane did something which I'd actually thought of doing, and I never did the calculation. I thought it obviously won't work. They took two copies of my model and put them on top of each other, one with upspin electrons going one way and the downspin electrons going around the edge the other way, and I'd have thought that these things would mix and scatter, but there was a new topological invariant, which was something like -1 to the Chern number, that hadn't been appreciated before. So this was an extra topological invariant, not the one that Barry Simon had pointed out was what the TKNN formula was, and that has led suddenly to generalizations to 3 dimensions and people discovering lots of very interesting topological materials lying in laboratory shells. Okay, so there was this toy model, which is somehow a relation to the TKNN story, again has a very fruitful history. It's also been translated into photonics, and there's a field now of topological photonics where you get light to travel one way around the boundary of things. Okay, so the third thing, if I have time, I'll talk about. How much time do I have? 10, okay, is the magnetic chains, which also is about the same time, about probably within a few months of the quantum Hall measurements by Klitzing. All at this time, things are coming out, and this was actually been baptized by Xiaogan Wen, who's recently made a very exhaustive classification using very fancy mathematics of cobordism or cohomology or something to classify all possible subsets of topological things. And this, in some sense, is the hydrogen atom of topological materials, it turns out. Okay. Of course, I did not know that at the time when I found it. But it was something totally unexpected. And of course, that's the hallmark of topological materials. They differ fundamentally by some number being 1 or 2 as opposed to 0, which gives them a property that's not present in normal matter, and this stuff behaves very differently from what was expected to happen. Okay. So actually, this was an interesting case. I actually was unable to publish it at the time because these two journals dismissed this out of hand based on referees saying, it's in manifest contradiction to fundamental principles of physics, a bit like what happened to Paulus and Luttinger that I mentioned. And by the time it was published, there was actually a more sophisticated argument that actually removed what I realized had been the connection to the earlier work that we're going to hear next from Kosterlitz, the Kosterlitz-Paulus transition, because there's a very nice mapping from two-dimensional classical systems at finite temperature, where there's a Boltzmann factor describing a probability weight, to quantum mechanics in one space and one time dimension, where the Boltzmann factor gets replaced by an amplitude. And quantum mechanics is richer than classical mechanics because Boltzmann factors are always positive, while in this case there may be some time reversal invariance, but the amplitude can either be positive or negative, and you get interference effects between one path having a positive amplitude and the other half a negative amplitude, and therefore the two things can actually cancel some process completely. So the thing was, in this paper I see that, my lost preprint, because I didn't have any records of it, it was just cited in people's work at the time, but Jieno Sholyom I found had finally kept a copy of it, and in fact it's kind of interesting to read it again, and it's actually basically using the Kosterlitz-Paulus argument translated to quantum mechanics to say why the conventional wisdom at the time was incorrect. Okay, you can find it on the archive if you want now. I posted it. So in magnetic chains, we have ferromagnets where they like to line up, or antiferromagnets where they opposite case. And this work dealt with a antiferromagnet in one dimension. Okay. And the feature there is what was known at the time is that the ferromagnet's got a conserved angular momentum, conserves its total spin, so it's kind of stable ground state. But the antiferromagnet, the quantum fluctuations in one dimension destroy long-range order. So people knew that as a mathematical theorem, but they had a remarkable thing. There was an exact solution of this magnetic problem for spin 1/2 system by Hans Bethe, who incidentally was David's thesis advisor at Cornell. And before he went off to tell us how the sun produces energy, he was interested in quantum chains. And he did a remarkable piece of work whose significance I'm sure he didn't understand, because he lucked onto a solution of this model that seemed to work, and it took about 50 years to discover why it worked. And Bethe clearly didn't understand why, because his paper says, my next paper will do it in 2 dimensions and 3 dimensions, but of course that never happened because this is a very specifically one-dimensional thing. But this was a very obscure, a difficult piece of work, and no one knew how to calculate anything else except energy levels from it. But in the mid-1970s, another piece of work, a remarkable piece of work, going back to the 30s, a Jordan-Wigner transformation, which maps spins, which are bosons really, to fermions by relating spin up to be filled and spin down to be empty states, gave a way to translate these spin chain languages into fermion language. And this actually was a lot easier to do calculations with than the beta ansatz, and it allowed one to translate things into calculations you could do. And I guess progress always happens when you can actually turn something to some calculation you can actually do on a piece of paper or understand. Then you can understand all the details. And this was done by Luther and Peschel. Luther was at Nordita for a long time after that. And they turned this thing into a fermion problem. And to cut a long story short, they got most of it right, but they missed out some detail, which I discovered later by applying this Luttinger liquid theory that was mentioned. And I found that that they didn't really have an understanding of what happened when you went from an easy axis to an easy plane to easy axis antiferromagnet, where the spins were in the plane or wanting to point out of the plane. And looking at the numerical, this new tool gave us a thing to extract numbers from the beta ansatz calculation. They showed immediately some term was missing. And these pictures here are actually exactly the quantum translation of the Koslett-Thouless story that Michael will tell you about. So it turned out that the spin half system was special rather than the spin one system. They both were Koslett-Thouless transitions, were driving you from an easy plane to easy axis, but there was a special cancellation effect, which I guess we'll vaguely say here, between in the spin half case. Here you've translated what Mike's going to tell you about from a two-dimensional space to a space-time diagram, and here there's a tunneling process that takes you between a configuration where these are compass needles in the plane. They kind of stay in the plane, and as you go around its periodic boundary conditions, you go around. In the first case, there's no kind of winding number. The second case, there's a twist that's gone in, like a Mobius strip or something. A twist went in, and you can't get from those two things continuously. You have to do some kind of breakdown, and there's a tunneling point, which is a vortex. And it turned out that for the spin half case, you only got a double vortex, because if you have to do this process of tunneling on one of the bonds between the spins, and if you look at the process on two neighboring bonds, everything should be identical if the bonds were identical strength, except the two paths. In one path, one of the spins rotated 180 degrees clockwise, and the other one it rotated 180 degrees anti-clockwise, so the difference of the paths is rotating a single spin 360 degrees, but if it's a half-integer spin, you get a -1 factor. So the quantum mechanics told you something. So looking at this way gave you a completely new way to look at things, and it turned out that the conventional wisdom was completely wrong. And finally, so we came up with this new story which shocked people at the time because it conflicted with preconceived notions based on the beta ansatz equations seem to confirm incorrect ideas about spin waves. And finally, let's not go through this too much, but at the end of the day, this turned out, this new state with this gapped integer spin liquid state that I found turned out to be one of the simplest topological states with a very non-trivial entanglement. The spin one system. And the interesting thing is the spin one can be viewed as two spin halves glued together. And in the usual case, they just point in some direction. But here, the spin one again splits, fractionalizes into two spin halves, which one on either side. And they grab onto the spin one half from the partner, and the next one along, and get entangled into a singlet state. And when you do that, you get left. The two spins at the end of the chain, they get left with one arm stretched out here and the other arm stretched out here, so there's like two half spins at the end. This is two unexpected spin one halves at the end of the thing, and this is precisely the analog of the edge states in the quantum Hall state. Again, this feature you find in all the topological states, that there's something strange happening at the boundary where the edges are, where things go from something to normal. So anyway, so that brings me to basically the end of the story. I couldn't really give you all the technical details, and it's probably quite confusing because it's very difficult to explain this to a general audience, even a general audience of scientists if they're not condensed matter physicists. But basically, my interpretation of why this prize was awarded now is because so much has suddenly, in the last 10 years, has come out of all this old stuff. These various little findings, which in each turn came from people finding something more amazing than they were looking for, they noticed something strange, and it gave you a new way of looking at things. And what's happened is that over my lifetime in condensed matter physics, I've seen that the kind of things we were taught and learned from textbooks like Ashcroft and Mermin and things back in the 70s, a lot of the details that were thought to be really important then are really, we put them away as boring stuff which doesn't relate, not important, and all kinds of new things like entanglement and new ideas which were not present in any of this old stuff have become the central kind of questions that we're struggling with. And this after the topological materials started to be found concretely as real things, there was also proposals that they could be used as a so-called platform for topological quantum information processing, and that, of course, has stimulated a large amount of interest. And there's been a huge amount of people in cold atoms, quantum information, condensed matter, even the string theorist, Ed Witten, is now devoting part of his time. I guess string theory is, there's some spare time out to deal with other things now, and they're getting very interested in extending all this topology to 4 dimensions. So we now have tables of topological matter up to 8 dimensions. So you can see how the influence from outside the field has influenced things. But this is a very exciting area because we're finding all kinds of what I consider neat stuff about quantum mechanics that we didn't know before. And there seems to be plenty of new insights to gain. So that when you can find something very simple and beautiful, we all think that's the truth, and maybe we're going to learn a lot about matter and learn a lot about possibly applications of it. Thank you.